All right. So let's talk about that assignment from yesterday on inclined planes. It should have been relatively simple. Okay? Relatively simple. Haircut? That's cute. Okay. All right. I threw over systems. I know to recognize that. Okay. Otherwise, I got it. All right. So when you look at 5 through 8, okay, either depending upon how you answered 4, that means that's going to drive the signs on those values. So if you're making down negative, fine, stick with it. If you're making up negative, stick with it. Okay? So I don't care how you do it, just make sure that you're consistent all the way through. On number 8, because that all kind of builds off of each other, both your net force and your acceleration should be less than 1. Okay, not a whole lot, but it should be less than 1. So both of those should be less than 1. Your answer to number 9 would be a phenomenal GPA on a weighted GPA scale. And your answer to number 10 is something around your first teenage birthday. Your first teenage birthday.
Which one?
I'm sorry. Number 10. Okay. All right. On your diagrams, make sure that I have the forces labeled. Okay. Do not just randomly draw arrows and think I know what they mean. And pay particular attention when you're drawing that force normal. That normal force has to be at some semblance to a right angle to this inclined plane. This normal force isn't pointing straight up. Okay, so when you draw that normal force, that needs to be, you don't have to draw it out exactly with the straight edge and measure it with a protractor, but I at least want to be able to clearly see that you're at least trying to make this thing look like a 90. Okay, and not like this or not straight up, pretty close to a 90.
This one is that one. This one.
Anything else on that? Once, twice, so. Get those handed in. Slight technical difficulties from back to the flip camera again. Okay, so here's the drill. Okay. So, I'm going to know my value of Fg. I can hang up the block and get the reading, right? Start with the 2.5 Newton scale. If the 2.5 Newton scale will do it, stick with that. So, if I know my Fg and I know my angle, I can calculate my force parallel. So let's just say my force parallel is 1.5 newtons, okay, just to make up a number. So, if I have to apply 2 newtons of force to pull it up, and I got a force parallel of 1.5 newtons, my force friction has to be
½ Newton.
½ newton. So basically your frictional force is going to be the difference between your applied force and your parallel. Now, how are you going to get your normal force? Fg cosine theta. So this is what you're ultimately after, is this. But you're going to measure the applied force, you're going to measure Fg, calculate the force parallel, determine the force friction, determine that coefficient of kinetic friction.
So the force friction and force parallel will add to your force applied only if they're at a constant velocity?
Yes, and that's what you're going to pull at a constant velocity.
Okay.
Otherwise, you're accelerating, and then that's going to get weird. Okay? All right? Okay, so stop that for a second. Let me hand out you. All right, so here's the second part of the lab. That's going to kind of involve some new stuff, but some old stuff as well. So here's the basic idea. You're going to take yonder block of wood, and these have to be specific to this, and there's a side that says top. That's where you're going to put on the top. Okay? And you take that and put that underneath one end, and then you're going to get a reading. You get a very specific reading. Call me over, take my phone, get that value. So the first thing you're going to do is just going to take this part, okay, and you're going to let it roll down, and you're going to get a value of 2 different accelerations. You're going to calculate the theoretical acceleration, assuming that this is an inclined plane. So you can use A equals G sine theta. Or you can take, oh, here's my force parallel, divide it by the mass, get it that way. I don't care how you do it. So you're going to get a theoretical acceleration. Then you're also going to time it over a certain distance, where then you can use that x equals 1/2 at squared plus v naught time. So you're going to get a theoretical acceleration based upon the angle. Then you're going to get an actual acceleration based upon data. Okay? And lay out all the distances, you know the drill, time it, boom, here you go. So that's the first thing that you're going to do. Now, the second thing you're going to do is going to involve these magnets. Okay? These are expensive magnets, and they are extremely powerful. Okay? Do not let the group beside you, do not let their magnets come close to this magnet. Okay? I'm serious. I mean, these will, if you let these two magnets get together, like they come together, they're that strong, you get your finger in between, it will break your finger. Okay?
Yeah, let's do it, Hambo.
How about no? Okay? I'm not going to risk these brand new magnets and all the time that I put in building all of this so you can screw around. I swear, so help me. You screw around with these magnets, I'm just going to kick you out of this lab. Okay? No exceptions. I'm not going to risk someone getting hurt because you feel like the urge to be an idiot. Now,
I like the Italian pants match.
okay, so to give you,
Oh my Jesus.
okay,
Where can I buy these?
Yeah.
go to Amazon.
Oh, yeah.
Okay, these, and magnets are rated on pounds. These are like 140-pound magnets. So theoretically, you could put this in the ceiling and attach a 140-pound person to it, and it would hold them up. Okay, so they're pretty strong. So, with that said, all right. So here's what you're going to do. Let me explain what this is made out of. These are two plates of aluminum. Aluminum is called a non-ferrous material, which means that this magnet isn't attracted to it. It's a non-ferrous material. Okay? So this stuff isn't magnetized. So what you're going to do, though, is if I take this magnet, though, and move it around on the outside, like this, nothing happens. But if I take this magnet and move it through the inside, I can make it move. Okay? So here's what you're going to try and do. You're going to try and find the value of the force generated by this magnet moving through these non-ferrous plates. So here's what you're going to do. Take this, set this up, and you want this thing as far away from this pole as you can so that it isn't attracted to it and interfering with it. So what you're going to do is you're going to set this up. Now, these are 1 inch wide. These plates are theoretically 1 1/8 inches apart. So you have about a 1/16 of an inch tolerance on each side. So you want to make sure when this thing rolls through, set that back underneath it, would you? Beautiful. So that when this thing rolls through, that it's not touching the sides. So what you're going to do is you're going to get this set up like this, and then you're going to let it roll through. But it cannot touch the sides as it goes through. So you're going to have to line up that track just right so that when that thing rolls through, it doesn't actually touch the sides.
It looks like it's going to bend from this side.
And you can bend these because it's aluminum. So if they're a little bit too close, you can just take them and like bend them apart. There we go. That's going to roll through like that. So what you want to do is that you're going to do a series of trials. So you're going to basically run this thing through without this magnet in it. Get an idea of what the acceleration is. Then you're going to run it through with that magnet in there, and the times should obviously be a little bit smaller. So what's the only way that this, which direction does the force have to be generated to make this thing go slower?
The opposite.
Of?
Gravity.
How about just the opposite of motion, right? So if this thing is coming along like this, right? My opposing force has to be acting up. So
Opposite parallel force, guys.
but if I push it this way, basically this thing comes to a screeching halt. If I push it that way,
Oh my gosh.
okay? But if as soon as it's out of there, if I give it any kind of push, it rolls forever. So this is actually the system that we use on some roller coasters as a braking. It's called an eddy current. So what happens is that basically nature hates an electric field. So here's the short version of, without going through a 2-day lecture on electromagnetic theory. Basically, the aluminum senses the magnetic field that's being generated by the magnet. It says, oh, this is bad, and so what it does is that it induces a current in the opposite direction to oppose the change in the magnetic field. So basically what you do is you get an interaction of magnetic fields. But it only works when it's moving, because if this thing is just sitting here, there's no change in magnetic field because everything is stable. So this only works when this thing is moving through. So there's a couple of things you're going to do. You're going to take this, first off, and I kind of take you through all of this. You're just going to let that swing back and forth. Okay, not a big deal. Then you're going to do that, and then have it swing inside the magnet, inside those plates, and you should see that basically it goes whoop, comes to a screeching halt. Now, we haven't talked about energy yet. Nature always has to conserve energy. So when this thing is swinging like this, it has a certain amount of kinetic energy. So when it goes in there, that energy has to go somewhere. And that energy gets transferred into inducing a current inside those plates that opposes that motion. So here's what you're ultimately after. You're going to try and figure out the value of that force that impedes that motion going down the inclined plane. So there's two distinct parts to this lab. The normal inclined plane with the boards that are over there and the blocks. Get that data. Then get the data for this. Then start answering all the questions. Now, there's two distinct sets of drawings that you have to do, both to scale. One is for the kinetic friction when you're pulling it up at a constant velocity. There's that one, and then there's going to be a set of drawings for this to scale that shows everything. Now, one of the things you're going to need is the weight of this. There's a little hook here. Take a 10-Newton scale, hang it up. You're going to get the weight of this whole system. And then before you can get the mass, and then you can do everything else. Okay? Good, fantastic, got it? Yes?
How do you find so we need to find the force that magnet applies?
Yes. Yeah, I kind of take you through it step by step.
You're
I
such a
kind of
nice
take you
guy.
through it. Okay, all right, you're on your own. Go, be free.